Okay, hello everyone. Today we're going to introduce the BFD basics. And about BFD, firstly, let's see some technical principles of it. A network may use private lines for different operators. And if one of these links is disrupted, the devices at two ends cannot detect the exception because the interfaces are still in upstate. So in this case, the routing protocols on the device cannot detect the exception as data forwarding cannot be switched to the backup link, resulting in the data forwarding black hole. So in this case, we can use the BFD to provide a low overhead, short duration method of detecting status of the forwarding paths between routers. And adjacent routers use BFD to quickly detect the failures in the following paths. Adjacent routers use BFD to quickly detect the failures in the forwarding paths, expecting the switch over to the backup forwarding path and improving the network stability. So about the BFD, after knowing the function of it, let's see a background. On some networks, devices are connected using operators' private lines. In this case, we have two routers, R1, R2. And they are connected using different routing protocols or static routes. Operator A's link is the main link. Operator A is the upper link you can see in this figure, right? And this is the main link. Operator B's link is the backup one. Failures in the main link will bring serious problems. For example, if we use the static route, although the main line is 40, static route remains valid because the status of the interface is still up, so the static routes remain valid. Services will remain interactive because data forwarding cannot be switched over to the backup link. And if we use OSPF, since it's a dynamic routing protocol, so when the main link breaks down, it takes about 40 seconds to tear down the OSPF neighbor relationship. It means that OSPF can figure out the problem or can figure out the fault in the network, but it takes about 40 seconds to recover. Right? Services will remain interrupted during this period. And for BGP, it's similar, but the time it takes even longer. It's about 180 seconds. So to solve these problems, we can use the BFD. It provides a standard method of fast path failure detection for all media types and protocols. It has the following advantages. First advantage is that BFD provides a low overhead, short duration method of detecting failures in milliseconds. Pay attention here. The duration is in milliseconds. It's much shorter than the time that OSPF or BGP takes to figure out or to tear down the neighbor relationship. And at the same time, it has high reliability. BFD supports detection of various failures in the past, including the interfaces, data links, and forwarding engines. It has no hardware dependencies and provides real-time failure detection for all media types and protocols. This is a background of the BFD. Right? And then let's see. The BFD provides a failure detection method independently of all media types, encapsulation formats, and upper layer protocols. And here you can see a figure. We have two routers, R1, R2. Between them, there is a switch, SW1. And let's see how does the BFD works in this scenario. BFD sets up a session between two routers, R1, R2, by sending rapid failure detection notice to the routing protocols in the local router to initiate the routing table recalculation process. BFD contributes to greatly reduce the overall network convergence time, and it cannot discover neighbors and needs to be notified by the upper layer protocol of which neighbor is set up a session with. The following uses OSPF as the upper layer protocol. So let's see the whole process. On R1, R2, we are running OSPF, and then after enabling OSPF, these two routers will set up an OSPF neighbor relationship. And after setting up the OSPF neighbor relationship, the protocol OSPF will send a notice to BFD. You can see both R1, R2, the OSPF will send a notice to BFD to ask BFD to initiate a session with the neighbor. And after receiving it, BFD will set up a BFD session with the neighbor. So until now, we have already set up the BFD neighbor relationship between R1, R2, and they will maybe exchange some packets or exchange some messages to maintain the BFD neighbor relationship between them, right? Well, BFD sessions can be set up proactively or passively. So proactive or passive session setup modes are two different modes supported by OSPF. Let's see the difference between them. If we use a proactive session setup, the local BFD proactively sends a control packet to initiate a BFD session regardless of whether it has received a control packet from the peer BFD. And pay attention here, only proactive setup is supported on Ruijie networks device currently. And different from the proactive setup, passive session setup is that the local BFD does not send a control packet until it has received the control packet from the peer BFD. Okay, and after knowing the two different modes of session setup, then let's see the process. After receiving a notice from the upper layer applications, for example, after receiving a notice from the OSPF, R1 and R2 BFDs send a control packet indicating down state to each other. You can see, since right now, both R1 and R2 are at the BFD down state, and they will send a notice or they will send a control packet to each other. And after receiving it, after receiving the control packet indicating down state, R2 changes the local session state from down to init. You can see from down to init. And R1 is the same from down to init. And send a control packet with STA set to 2. Here, STA represents state. Is one of the fields in the BFD control packet, right? It indicates init state. R1 changes its BFD state in the same way. Okay, so you can see here, both of them send out BFD init, right? BFD init control packet to each other. And after receiving the control packet indicating init state, R1 changes the local session state from init to up. And for R2, it's the same, from init to up, here, from init to up. And at the same time, send a control packet with STA set to 3, including up state. R2 changes its BFD state in the same way. So you can see both of their states are up, right, from init to up. So both R1, R2 BFD are in up state. Session is set up successfully and starts to detect the pass failure. This is the session setup process. And this process is called, it has a name, it's called three-way handshake. Okay, so BFD set up the session between each other through the three-way handshake. And no matter down or init or up, we have mentioned are all the states of BFD. So let's see the BFD finite state machine. BFD sessions have 3 basic states: down, init, and up. For the session is in down state, let's see, BFD changes to up state when receiving an init packet. And BFD changes to init state when receiving a down packet. Or the BFD maintains its original state when receiving other types of packets. Okay, so you can say from down to init, there is maybe a down packet. From down to up, here is an init packet. For other packets, we will maybe maintain the original state. And for the session is in the init state, you can see in the init state, it changes to up state when receiving a init or up packet. You can see init or up. We will maybe switch from init state to up state. And BFD changes to down state when receiving an admin packet. Or for other types of packets, we will remain or we will maintain the original state. And for the session in the up state, changes to down state when receiving an admin or down packets. While for other packet types, we will maintain the original state. Okay, this is the switching of states between maybe different between down and init, down and up. Okay. And then let's see the failure detection of BFD. Since we have introduced the process of setting up a BFD session, and after successfully setting the BFD session, BFD will maybe start the pass failure detection, right? And let's see how that works. Now, the link between R1 and SW1 is disrupted. You can see here it's disrupted. And then R1, R2 BFD session detect a pass failure, set the session state to down. So firstly, BFD will detect the failure. And once BFD detects the failure, the state of the session between R1 and R2 will be turned down. The BFD session will be turned down. And then BFD notifies the local OSPF process that the BFD neighbor is no longer reachable. Since the BFD neighbor is no longer reachable, means that the OSPF neighbor should be set to down. Okay, so the local OSPF process tear down the OSPF neighbor relationship. If a backup path is available, data forwarding will be switched over to the backup path. So in this case, you can find we don't need to wait for OSPF to find out the fault in the path by itself. Right? BFD will figure out the failure in a very short time, in milliseconds, and then will notify OSPF that the fault in the network. Okay, and next, for the failure detect, BFD supports different modes. First is called asynchronous mode. Let's see how does it work. Systems periodically send BFD control packets to each other. And if a system does not receive a packet from its peer within the specified period, pay attention here, it mentions a time it takes. It's called specified period. But exactly how long it is, later we will introduce it, okay, how long it takes. And it clears the session to be down. The asynchronous mode is the mode which is only supported right now on Ruijie networks device. Okay, and except the asynchronous, the other mode is called demand mode. Each system has a unique method to check its connections to other systems. The system stops sending BFD control packets upon session setup. And except that BFD supports another function, equal function. The local system periodically sends BFD equal packets that are forwarded back by the remote system along the same path. This method does not require involvement of the control plane of the remote system, reduces delay, and delivers faster failure detection compared with the control packet-based detection. So by using the BFD equal function, now we assume that we have two ends, right? We have two ends. Okay, R1, R2. If we enable the equal function, R1 will send the BFD packet to R2, and R2 will not, actually here, pay attention, R2 will not process this packet, while R2 will directly maybe send or forward the packet back to R1 through this CM path. So in this way, each time when R1 send out a packet, R1 can receive it, means this path works normally, right? There's no fault. And the neighbor R2 is reachable. So in this way, we can ensure that this path working normally, right? So you can think that since R2 don't need to process this packet, so there's no requirement on R2 about BFD. Even R2 can maybe do not support BFD. It will not affect actually. Okay, it's a equal function. And if we use the equal function together with the asynchronized or demand mode, let's see what will happen. If we use the equal function together with the asynchronized mode, when enabled in the asynchronized mode, equal function will perform detection of failure, greatly reducing the control packets. While when enabled in the demand mode, equal function allows the system to get rid of control packets entirely upon session setup. Okay, this is application of the equal function. And next, let's see. When we introduce, no matter the setup of BFD session or the maybe past failure detection, we have mentioned the BFD packets, and we say it supports different functions, it have different fields. So at this part, we are going to introduce it in detail. Let's see it. For the BFD packets, the first type is equal packet. BFD has no requirements on the equal packet format because they are used only by the local BFD process rather than by the remote system. While different from that, for the control packet, BFD defines a format, which you can see in this figure. Right? Currently, control packets have two versions of formats, version 0 and 1. By default, we use version 1 format. And it's just, as you can see in this figure, it contains multiple fields, for example, versions, diagnostics, states, right? For detect multi, length, auth length, auth type, and so on. About these fields, let's see them one by one, okay? First field, VER, is actually its version, is 3 bits long. It's a version number of the protocol. Currently, the value is 1, right? And the DIAG is a diagnostic. This code specifying the local system's reason for the last change in session states. Then STA is a state. It represents the local BFD states, and the options could be 0 or 1, 2, 3, right? It represents different states. And the next bit, or right, P is 1 bit, indicates whether the transmitting system is requesting verification of connectivity or of a parameter change and is expecting a response. And since the length is 1 bit, so the value could only be 0 or 1. And if it's 1, means yes. If it's 0, means no. Okay, for the following bits, it's similar. 1 reference yes, 0 reference no. Okay. Next bit is F, which is final, indicates whether the transmitting system is responding to a received BFD control packet that had the P bit set to 1. And then C, control plane independent, indicates whether the transmitting system's BFD is independent of its control plane. And A is the authentication person. In case whether the session will be authenticated, right? The operations are 1 reference yes, 0 reference no. Okay, and D indicates whether the demand mode is active in the transmitting system to monitor the session state. M is the multi-point. This bit is reserved for future point-to-multipoint extension to BFD. Of course, nowadays, BFD only support the point-to-point network. Okay, next field is detect multi. Detection time multiplier used to calculate the detection timeout interval. In demand mode, the value from the transmitting system is used. In asynchronous mode, value from the receiving system is used. You can say it's different. So since nowadays we only support asynchronous mode, so you just need to remember that the value is determined on the receiving system. Okay, and then it's a length, packet length, right? It's quite easy to understand. And next, my decryptonator is unique, right? And this value generated by the transmitting system, which is used to distinguish multiple BFD sessions of a system. And your discriminator, this discriminator received from the corresponding remote system and reflects back the received value of my discriminator, or is 0 if the value is unknown. Okay, and next, desired min TX interval is 32 bits, right? Is a minimum interval in microseconds that the local system supports when transmitting BFD packets. And for the RX interval, is also 32 bits, right? And it's similar, actually. It's a medium interval in microseconds that the local system supports when receiving BFD packets. So transmitting and receiving, it's the difference between them. And next, required min equal RX interval. From the name, we can know actually is useful for the equal function. Right? It's also 32 bits, and it's a minimum interval between received BFD equal packets that the local system supports. Right? And next are some fields related to the authentication. First is the authentication type, BFD control package authentication type. While now currently Ruijie networks does not support BFD authentication. And auth length 8 bits is the length of the authentication section, including the auth type and auth length fields. And the next field is authentication data. It's the authentication section load. Some parameters used to authenticate. Okay, here are some fields in the BFD package. And if you can use the maybe a capture tool to maybe capture some packets and check the fields inside, as you can see in this figure. Okay, after introducing the technical principles, next let's see the BFD configuration. Okay, firstly is the example of the static routing. We're configuring BFD to support the static routing. In this figure, it shows the interfaces and IP addresses of R1 and R2 that are connected using 2 per-bit lines from different operators. The configuration requirements are as follows. Line A is the main line, line B is the backup line. So to set the maybe the main line and the backup line, we should, if we use the static route, we can change the preference value, right, to achieve that. And the length where 10.1.1.0/24 and 10.1.2.0 are located and connected using static routing. Data forwarding can be switched over to the backup line when the main line is disrupted. Okay, to switch over, we should use BFD to detect the fault in the network, right? So let's see the configuration. On R1, Firstly, we are configuring two static routes. And for these two static routes to the same destination, you can see to the same destination, the interface or the outbound interface is different. The next hop is different. So in this case, we have two paths can use. And since we only need one of them to be main line and next is the backup line, so we have changed, you can see the preference value of the second. In this case, normally when you check the IP routing table, you can only see the maybe route entry, which next hop is 1.2, right? And if the main line is 4, so we will switch over to the next entry. Okay, this is the configuration of static routes. And then interface range G00 to 1. So we are configuring two interfaces at the same time. And actually, this is a configuration of BFD. Let's see the command. BFD interval 100, min RX 100, multiplayer 3. Here, we set 3 numbers. BFD interval 100 is the transmitting interval. Min RX 100 actually is the receiving interval. Multiplayer 3 means that we will wait for 3 times of the interval. When, for example, when we cannot receive the packet from the neighbor. So in this case, it takes about 300 milliseconds. Okay, and next, no BFD equal. We are disabling the BFD equal function, and this is necessary because this function is enabled by default. And the last step, you can see IP route static BFD G00.192.168.2.2. So it means we are applying BFD to the static routes, right? And IP route static BFD G01.192.168.1.2. Okay, this is the configuration of BFD, right, to support the static route. You should understand the function of each command inside. And next, configuring BFD support the dynamic routes. Dynamic routes could be maybe OSPF or BGP or RAID. So let's see it. Interface G00, BFD interval 100, min RX 100, multiplayer 3 is the same. Right? No BFD equal is the same as what we have configured. While which difference is here? IP OSPF BFD. By using this command, we configure BFD support for OSPF, IP RIP BFD. So config BFD support for RIP for RAID. And for BGP, it's a little different. Router BGP subnet neighbor 101.101 for over BFD. We're configuring BFD support for BGP 1.101 is a neighbor. Okay, so this is about the configuration of BFD support for the dynamic routing. And after finishing the configuration, we should verify the result. So by using the command show BFD neighbors, you can see our address, neighbor's address, right? And for example, the state is up. When we verify the results, firstly, we should check if the neighbor is what we have configured. And except that, we should confirm if the state of the BFD session is up, right? And for these fields in this table, you can see our address represents the local interface address. Neighbor address obviously is a peer interface address. LD, RD is the session ID in the local and remote system. RH, RS is the session state in the remote system. And the hold down mode is a timeout interval for the local system to receive a hello packet. And that is the number of times for detecting sessions timeout. And next field state is obviously session state in the local system. INT is the interface, right? ID of the interface where the session is located. Okay, so this is about the configuration of BFD. And for this part, let's see some questions. The first question, BFD can work independently of other protocols. You think it's true or false? Actually, it's false, right? Because we see that BFD cannot discover the neighbor by itself. So if we use it maybe to work with some dynamic protocols, for example, OSPF, so OSPF will discover and will establish the neighbor relationship first, and then will notify, will send a notice to BFD, and then BFD will set up the BFD session. So this is false. BFD cannot work independently of other protocols. Okay, so about the BFD, let's make a summary. On networks with private lines from different operators, line inspection may cause data forwarding black hole, and BFD can detect failures in the forwarding path and notify the upper level protocol of conversion on a new path. And this document describes in detail the BFD control package structure, technical principles, implementation mechanism. Also provides examples for configuring BFD support for other protocols and check the BFD status. Okay, that's all for this part about the BFD basics. Thanks for your time.